All right, guys, let's work on number 4. I kind of started on this without starting the video, so sorry about that, but let me just quickly explain. I know that this is a single replacement because I only have one element here, so single replacement, right? Then I have to determine, since this is a single displacement, then I am going to go with the activity series to determine if I'm going to have a reaction or not. So the only thing I have to worry about is this one strong enough to knock over that one? And the answer is yes, because this is group 1 or 2, and that one is a transition metal. So replace that one, and I am going to get magnesium nitrate, and I know that magnesium is a 2+, and then this nitrate is a negative, so that's why the 2 here. And then I'm going to say another one I'm going to get is iron, and it's going to be solid because iron is by itself and it's a metal and it's just sitting there by itself. It's not an ion, so solid. Now I know that all my nitrates, this is the can ones, the chlorate, acetate, nitrate, they are all going to be soluble according to my chart right here. Can ones are always soluble, so no precipitate, so it's aqueous. Now let's move on to the next step. The next step is to just write out anything that was solid. You keep solid, gas, and liquid, right? You disassociate the aqueous. So my first step is to just write down all my solids. Since this is a solid, it's not an ion. Remember, if it's a solid, you're not going to put a charge. So let's put ourselves a reminder here. Solid, liquid, gas, no charge in the net ionic equations, okay? This is a solid, no, nothing. So then on the other side, I also had a solid, which was iron. Just put that and nothing more. Now remember, whatever I have on one side, I must have on the other. So how in the world did I get to iron if I only had magnesium? That's where my ions come in. Only the ones that actively participated. This is a spectator ion. I don't care about that guy. So I'm going to say, well, the reason I'm able to have iron on this side is because I had an iron ion. So in this case, it's an ion, so I got to give it a charge. Now, what's the charge for this specific iron? And the answer is 3, because it's right here. And I'm going to say, what's the state for this one? Well, this one came from this, so it is aqueous, okay? And I move on to the other side. So iron and iron are matched up. I need to do something about my magnesium, so what do I do here? I'm going to say, well, magnesium from my product side came from here, right here. So magnesium then, it is going to be aqueous. And what was the charge? The charge is 2+, and I know that from looking at the periodic table. It's in group 2. Now the next step is to balance it. All the other problems from before, balancing was kind of easy, but this one is kind of funky because I see that this one is a 3+, so overall, let's pretend like this is an equal sign, okay? Right now, my charge is a 3, positive 3. And on this side, my charge is a +2. Well, they're not equal, right? It's either got to be 0 and 0, or it's got to be 3 and 3, or 2 and 2, but they're not equal. So how can I make these equal? Well, I need to make sure that I multiply this one by 2. Then on this side, I'm going to have a +6, right? If I do that, I want to make sure I multiply this one by 3. 3 times 2 is 6. So now I have 6 and 6 equal to each other, so I'm good to go. Whew. So these are balanced. But remember, whatever I have on one side, I have to have on the other. If I have 2 iron on this side, must have 2 on that side. If I have 3 on that side, must have 3 on that side. And I look at it overall, 3, 2, 2, 3. I know that I can't reduce them overall anymore, so this will be the net ionic equation that is balanced and single replacement. Just on the side note, if this were to be 3, 3, 3, 3, obviously you just reduce it to say 1, 1, 1, 1, but right now I can't reduce them anymore, so this is the right one.